Hello and welcome back to Calculus 1. We are still reviewing. So this is the second part where we discuss function composition, combining functions, inverse functions, all of those things that we are going to see a lot in this course in calculus. So function in the end gives you a number, a y value. So you plug in 3 and you get 7, and then you were looking for that 7. That's the result. That's the answer, right? And now that 7 could be whatever concept you're working on. So if I have, say, f of x, combining functions, oops. So let's say I have f of x to be x plus 3, and another function g of x to be x squared minus 1. Right? We need to understand immediately that if I am using, let's say, x equals 5, 5 is too much, let's go with 2. So x equals 2, f of 2 is 2 plus 3, which is 5, and g of 2 is 2 squared minus 1, which is 3. So as you can see, with a different function, I am getting different answer. Now it might line up to be the same number, but it worked out this way now. The key point here is that you are getting numbers at the end. So in some sense, this number, this function represents a number. Now what can I do with 5 and 3? I can add them, right? I can subtract them and multiply and square, and I can do all bunch of operations with 5 and 3. So what I can do here is I can say, well, f plus g, I can add these two functions. And if I add these two functions, I will get x plus 3 plus x squared minus 1 to give me x squared plus x plus 2. Now, as you can see, we obtained a different function that it's unlike any of the original functions. I mean, it's quadratic and one of them was quadratic, but it's a different quadratic function. And if you observe carefully, right, I can compute f plus g of 2, which would be 2 squared plus 2, and that will give me 4 plus 4 is 8. Don't you see if you add these two puppies you get 8? It has to click that way like a jigsaw puzzle. It has to. It doesn't matter if you compute each function individually and then you add, multiply, divide those answers, or you combine the functions algebraically and then compute the number. You have to get the same thing. Because you're using same functions, and you're using same operation, and in the end, function gives you numbers, so whether I'm going to combine those numbers individually or I'm going to combine them within the function doesn't matter. Now you can try this exercise with subtraction, with multiplication, and it will always be the same deal. So let's do multiplication as well, and be done. Hi, English 1, right? No?
Calculus.
Ah, you're what? You have diagonal seats. That one or that one? That one? Hold the wall, nice. No chair? Yeah. No chair either? Oh, I did everything I could. And he walked like half the classroom this way and that way, and then there's just, yeah. Where are the chairs, by the way? All right, she might. Okay, so multiplication. We can go f times g of x, and that means x plus 3 times x squared minus 1. And when you FOIL this, we get x cubed minus x plus 3x squared minus 3, and then f times g of 2 it better be 15. It better be 15 because f of 2 is 5, g of 2 is 3, 5 times 3 is 15. If this thing doesn't give us 15, we're just going to close our books and everything and just leave. Because it has nothing to do with anything anymore, right? Yeah, I see fingers crossed over there, but ain't gonna happen. So 2 cubed plus 3 times 2 squared minus 2 minus 3 is 8 plus 12 minus 5. I know, it's 15. It has to be. So you can compute individually, you can compute algebraically, and then plug in the number, and you will have the same value. So combining functions this way, you can add and subtract whatever amount of functions you need to, and they will all work together to give you this final answer at the end. But there is a very special way to combine functions, and that is to plug one function into another function, and that is essential to success in calculus. It's called function composition, and it's the central part of our derivative techniques with the chain rule and so on, and then later on the most important integration technique called U substitution. They all feed off of the function composition. And I am always open with my students, and you are my students. So if you are planning on not learning this, pack your stuff and quit now. Without this, there is no Calc 1. So here we go. You are going to plug one function into another function to obtain the new function. That concept is something that you do daily. You don't think about it in terms of defining it through mathematical terms. But if you have a backpack and you have a computer, backpack has a function to keep the stuff. Computer has a function to also store stuff and compute stuff and so on. You put the computer inside the bag. Right? Well, now the bag is heavier, it contains stuff, so it's not the same bag without a computer. You'll be much less upset if someone stole your empty bag than if someone stole your bag with the laptop inside. You'll be upset, but you'll be less upset, right? So these are the things that you think about now. You take one function, you plug into another function, obtaining a third function which might have or might not have the features of the others. And it will actually, the same domain. The most restricted domain is the domain of the whole new function. So the way this works is you have function f of x, which is, say, x squared plus 3. And you have function g of x, which is, let's say, just square root of x. Now, you can make the function composition by composing f with g, which is this symbol. It's not O, and it's not a dot. Dot is the product, and O will be a little bit like that, right? This is like degrees, but it's not. We write 90 degrees, but this one goes in the middle, right, as a notation. So we still, some people will say fog, but it's actually pronounced correctly. It's f composed with the g. So you have f times g, f composed with g, f convolution g. This one is in differential equations. So you have all these types of, and obviously f plus g and all of that kind of stuff, right? So there are these symbols, and they all mean different things. So this is a composition, and this means plug g into f. Now, I'm a visual learner. You just give me this and stop talking, and I'm 100% okay. Because visually, I know, because I'm a visual learner, that if I have f of x equals to, let's say, x squared plus 3, if you give me f of a flower, I have a flower squared plus, I don't need to understand it. I don't need to know what flower squared means. For me, visually, if you replace x with whatever the hell you think of, I'm just going to replace that x on the right-hand side with what you gave me, right? So now, my common sense, right, in observing the composition formula here, my common sense tells me that if I have f of g of x, it better be g of x squared plus 3. The function f needs to look the same as the original function, where every x is replaced with g. Now you can have multiple x's, each x needs to be replaced with the entire function g. So now g of x is root x, this needs to be squared, and then I have plus 3, and the whole thing works out to be x plus 3. So function composition takes the function f, plugs g inside, you worked out the algebra, and x plus 3 comes out. So that's what we have. So in this case, function composition, f of g of x was x plus 3. Now I can also have g composed with f of x, where g is the boss, and f gets plugged in, right? Now in this case, what is the function g? Well, it's clearly square root of f, because it was square root of x, but every x in my notation over here, the x that was in here is replaced by f. So simple replacement of x with f of x here triggers the replacement of all x's on the right-hand side with f of x. And now I know what f of x is. It's x squared plus 3. So this works out to be square root of x squared plus 3. I don't want to see any algebra voodoo, so you cannot take that square root there because of plus 3. That's... We'll see. So now we see that two functions, f and g, which are given, right? F composed with g and g composed with f give us completely different functions, right? One of them was x plus 3 and the other one was square root of x squared plus 3. So it depends on which functions you have and the way they are lined up together. Now there is a formula which you used in PreCalc 1 to solve the problems, and most likely your instructor never told you what that formula is for. It was just something for you to compute in PreCalc class. You did it, you moved on, and question is even if you remember it. Difference quotient, anyone? Yeah. And probably the menacing thing that you are remembering, right? Strikes the fear. Well, that formula has a combination of function composition and function combinations. So difference quotient was equal to f of x plus h minus f of x divided by h. And you were supposed to memorize this thing, and then when they give you the f of x, you were supposed to compute it. And then you have your grade and you go home, right? Whew. This is important for Calc 1. This, with a limit in front, becomes the definition for the derivative. And derivative is the basic building block of all mathematics that follows. And that's where difference quotient sits. Now, no one probably said anything about that in PreCalc 1. Said, here's the formula, just do some calculations and be done. Now, I'm still not going to talk about the derivative. That's going to be next week or the following week, right? Chapter 3.1. But I am going to compute this now as a PreCalc 1 review. So if I give you f of x is equal to x squared minus 3. My favorite, right? For today, I don't know. I've been using number 3 for the last few days. Too much. All right, let's take a look at the features of our formula. Well, first of all, I have f of x plus h. And then I have f of x. Ooh, well, that's f of x. So this and this is the same. Okay, so that plugs there. Great. But it doesn't plug here. I actually have to compile that part. So what is f of x plus h? There I say it's clearly, it clearly has to look like this, except this x is replaced by x plus h, therefore this x needs to be replaced by x plus h. So if we had the replacement of x with x plus h, then we have the replacement of x squared with x squared plus h squared. Now, unleash algebra. We have x squared plus 2xh plus h squared minus 3. And this piece is the one on top. So, let's do some colors. That goes there. And that goes there. And then you divide it by h. And then you follow the algebra. Right? So what do I have now? DQ. It stands for difference quotient, not Dairy Queen. All right? So difference quotient is equal to, we have this long division line. The first part is x squared plus 2xh plus h squared minus 3. Minus, in parentheses, the purple is x squared minus 3 original function. Everything divided by h.
You said 2 and you wrote 3 for x.
Whatever I said, I wrote it right.
Okay. Are you sure?
Oh, you mean this one?
Yeah.
Sure. Thank you. I was just testing you. Oh no, I do that all the time. So, which is going to be tough every time Hallie's not in class. I mean, then you're responsible. All right. So now we get rid of the parentheses, which would change all of the signs. So we have x squared plus 2xh plus h squared minus 3 minus x squared plus 3 divided by h. And if you did your math right, all of the terms that do not contain h will cancel. You have positive x squared, negative x squared, gone. Negative 3, positive 3, gone. The only terms that are left are ones that have h. And you can factor the h. You get 2x plus h divided by h, and then this h dies. And you are left with the difference quotient is 2x plus h. And this is where we leave it for now. There will be additional step in chapter 3 where you are going to say h is 0, so the derivative of the function is 2x. But that's chapter 3. So you are going to do 100% of this problem in chapter 3. We're also going to have some of these in chapter 2. And then you are going to have additional step. And this is one of those times when I can clearly show or prove to you that the pre-calculus is just going to be upgraded. So we are going to take everything you learned in pre-calc and put in a framework of calculus, you know, make things move, and so on. So that's the difference quotient. And the function composition. So for function composition, you are going to replace every x with the new function and then work out the algebra of that function. Now, I said that if you're not going to learn this and not going to understand this, that you are doomed. And you are. Because you are going to learn that the derivative of sine x is cosine x. And you will very rarely use derivative of sine is cosine because you are going to have derivative of sine e to the x. Now that's a function composition because e to the x is plugged into sine. And in order for you to use the formula, which is the chain rule formula for derivative, well, you need to know which one is the inner function, which one is the outer function, right, in terms of function composition. And once you're able to sort that in your head, you will be able to take the derivative using chain rule. For that, you must know this. So not just how to put functions together, but how to decompose, which is the next part, decompose function composition. Decompose function composition. Now, if I have, as I said, function y equal sine e to the x. Well, sine is a trigonometric function which must have argument in here. If there is no argument, then this is just a religious term, I guess. All right? But if you put something here, it becomes trigonometric function. Now, it's not sine x, basic trigonometric functions. This one is sine of e to the x, which is composition. Now, what is important for you to immediately start noticing is that e to the x is plugged in sine x, as opposed to e to the sine x, where sine x is plugged in e to the x. So this is crucial to understand. You had a little bit of this in your, well, not this type, but the difference between x squared and 2 to the x. Right? This one is a polynomial, and this one is exponential. Now, when you look at them, it's x squared or 2 to the x. It kind of almost looks the same, right? Even with, right, dyslexia, that could be the same, and it will be a really bad problem, right? Not to recognize the difference between these two fundamental functions. But if we put that aside and we talk about function composition, these are vastly different functions. They involve two of the same functions, but again, it's f composed with g and g composed with f, and they are not the same. They're not the same. So decomposing here is try to figure out what is this overall outline of the whole thing and what is the smaller function that it's plugged in. So on the outer side we have a sine x for the first one. So I would call that f of x, which is sine x, and then g of x is e to the x, which is plugged in. Clearly on the bottom one, f of x is e to the x, and g of x, which is plugged in, is sine x. And this is, again, making sure that these guys are composed as f composed with g. I'm going to separate these two examples with this thin line over here so that you are clear on the function decomposition. So let's see. Another example. You can just shout out the answer if you know it. It's fine. Y equals log base 3 of sine x. What's f? What's g? Yeah. Log 3 of x, and then sine x. How about e to the x squared? You're going to see this a lot, this one. So what's f? E to the x. What's g? X squared. Now if you're still struggling with this x squared will replace this x, and there you go. E to the x squared. What now? Cosine squared x. What's f? What's g? Nope. That will be multiplication. Cosine x times cosine x is cosine squared. It's not a composition. We need a composition. What happened? Nope. There we go. And what's g? Cosine x. Huh. Are we going what? Ah, thank you. Thank you. Because I was about to just leave. Right? Yes. Well, if we are composing f composed with g, she said g will always replace x's of f. Yes. But let's talk about this problem. Oh, this is so awesome. You know what I'm going to do? I'm going to rewrite this function for pre-calculus. Remember, pre-calculus, prerequisite, pre-calculus, calculus, pre-calculus, right? There's that word pre. Cosine squared x can also be written as cosine x everything squared. Now, is it clear now? Oh, yeah. When the whole thing is squared and you have a function in the middle, well, if you yank this out, what are you left with? You're left with this. So call it x squared, and now replace that one with a cosine x. You will get cosine x squared, and then you just write the way we are just used to writing the thing, because it's mathematically it's shorter to write than extra parentheses and squares, right? Just write x cosine squared. Same notation for ln. If you see ln, and you will see ln squared x, that just means ln x everything squared. Again, in a function composition, it's going to work this way. I am going to leave all of this here the way it is. And then if you rewatch the video or something, you should click in. But again, and I'm going to actually add to this in purple versus y equals cosine x squared, where f is cosine x and g is x squared. All right, stare at this. Stare at this and realize the difference of where x squared goes, where cosine goes, the way they're related. So for the black and red, which is the same problem, black and red is the same problem. Red is the explanation for black. Because we can write cosine squared x as cosine x everything squared, that means that the outer function, think of the layers of the onion. Anyone cooks? Yeah, we can change recipes. Onion has layers, like shells, right? So think about it, right? You have this layer, then you have another layer with a square, there might be another layer with +3 over here, there might be another layer with everything divided by h, right? So you can add as many layers of the onion, right? You have bigger onion, smaller onion, and all that kind of stuff, right? So whatever is the outer side of the onion is the one that you see, and that's your f. And whatever you can't see is the thing that's buried in the middle, which is the cosine x. Technically, right, this has parentheses, I don't know, visually for me, has parentheses over here, so that's the outside function, which is x squared, and then I can replace that x with the cosine to get this, which gives me that. Now, why are you weak with this? Why are you not just flying through these things? Because this is something you haven't practiced. If I give you two functions and ask you for composition, at this stage in the game, you should instantly give correct answer. Right? Maybe even without writing stuff down. But I'm sorry, we don't care about that in calculus. We need a backwards procedure. So this is the part where you go home and you start bleeding over the notebook, right? Because these things depend so much that you get it. So it is this skill that you have to practice, and it is okay to be bad at it now, because, as I said, you haven't dealt with this before to the extent that we need it now. But between this class and the next Saturday's class, there are 7 days, right? And in those 7 days, you are all going to earn at least masters in this, if not PhD, because you will make yourself sit down and keep decomposing and then chase me down, chase Ellie down, go to the tutoring center and make sure that you can decompose these things, because I'm sorry, there is no Calc 1 for you if you can't do this. And that's the bottom line. So, again, my office hours are listed on the first page of the syllabus. My office is 1 floor below your classroom. And I'm here 5 hours a week for office hours plus the clubs, and you can catch me also, you know, outside the classroom and the office, and ask these questions. But please, don't kid yourself that you can just, you know, cut corners on certain things that don't look cool the first time you saw them and be successful, because you won't. So study this example. I'm going to actually box this a little bit more, like box it off as a, you know, you have a different example here. And again, if you are to put parentheses around x squared over here, you will see that x squared is plugged into cosine because it was supposed to be cosine x. And then you replace that x with x squared. So that's the reason why the outer function is f as cosine x and the inner function is x squared. Yes?
Why can't we just write cosine squared x, and why doesn't it have to be cosine squared x squared?
That brings a completely new problem, and that was actually my next problem. So you might answer your question by thinking about this. This is the next step. Now, if you were asking, now this is what I would write on the side, because that problem. Where should I write this? Maybe, how about sideways over here? I can generate infinite paper to the side, right? Yeah, go ahead, do that in your notebooks. The problem is that if I do that and I start writing there, then when I make the PDF file, it won't fit your printing. It will just gonna make everything will be that small. It won't be able to read it. So I never swipe right to the side to make more paper that way. So I'm just going to write sideways, and you will deal with that. Cosine squared x is the same as cosine x squared, which is cosine x times cosine x. Cosine x squared is cosine, oh, are you kidding me? Of x times x. So I hope that made sense. And if you are now breaking your necks, you're welcome. That's also exercise included in price, right? On when the weather goes now, we're going to go outside and do push-ups and stuff. But for now, we'll just do calculus, all right? So cosine squared can be you can write it as cosine x, everything squared, and that means cosine times another cosine. Where this one, cosine x squared, well, it's just x is squared, so it's x times x. It's not cosine times cosine. So it depends, right? It matters where this square is. And now you get to experience that here. But there is another aspect of this problem that is a little bit evil, and we didn't talk about it yet. And that is what? How many functions do we have? How many functions do we have? 3. Very good. There are 3 functions. This onion has 3 layers. There is the, well, first I'm going to rewrite this so it's easier to see all the levels. Aha. Yeah. Sure. So, she was very particular. 2 seconds. We communicate. She hacks the exact thing. I think she got it. Huh? So hold your laughs next time, because we know we're professional. We know what you're doing. There are your levels, right? Now look at this. Wouldn't you all agree that this cubic function is the boss, right? The overarching over everything, right? Because we have these main parentheses around everything and then cube, right? So wouldn't you agree that's that? And then you dig deeper, right? So you have the upper level, and that's your f. So that's definitely x cubed, right? So you have your upper level x cubed because you just cover all this stuff up and just x cubed. Dig deeper. Now you are inside parentheses. Which one is the boss? Cosine or x squared? Cosine is the boss. So next level down, g is cosine x. And then h is just x squared. Shall we test this? Sure, why not, right? Take x squared and plug it in here. You get cosine x squared. Now take cosine x squared and plug it for this x, and you get cosine x squared everything cubed, and you can jump this cube on a cosine, and there's your problem. Now see, what I have in red, this is what you know, like this. So go ahead and write whatever function you want as a practice. Try to decompose, but because, and when you have the answer, what you think is the answer, try to compose it back the way you write it. Now you know that procedure. If you don't get what you started from, well, something is wrong, right? And please see me, because these concepts are essential for Calc 1. like 90% of problems. We utilize this on a like subconscious level, all right? I'm going to get rid of this so it's not confusing. You can check this. So I'll just write in blood here. Check by composition. And done deal. So you have all of these things. By the way, I never... Okay, it's working. I always ask someone to watch the stream in the classroom so they can tell me to restart if a network explodes or something. Generally, Ali does or whoever SI is, but then, you know, you can also put it on a cell phone or whatever. If you see it's frozen, sitting there for 2 minutes, for me, just a quick restart. Otherwise, you lose the entire hour and a half. It dies in the first 5 minutes. You know what I mean? So it's like someone, whoever. And you can do it actually on the computers in the desk. Pull it up. Good. So that takes care of function composition and, more importantly, function decomposition, so that you can do your chain rule and your U substitution later on, which is basic for integration. Yes?
You may have already answered this / I may need to already have known this, but how again are you able to write cosine cubed x squared equals in parentheses cosine x squared?
That's the knowledge from PreCalc 2.
Yeah.
So that's the knowledge from PreCalc 2, and if you don't know it, well, now you know it, right? So if you write, I also said there's one for ln, right? So if you have, let's say you have ln cubed of x, you can write that one as ln x cubed. So that's just the notation for these functions that involve letters, like sines and cosines, tangents, and ln, right? And that is something that you actually need to have as a prerequisite. Again, if you forgot it or whatever, not a big deal. You've seen it now, and keep it in back of your head. And just make sure you don't make the biggest noob mistake, which is to say that ln x squared is the same as ln squared x, because it's not, right? They are not the same. This one over here is ln of x times x, and this one over here is ln x times ln x. Those are vastly different things, right? So you have to make sure carefully, right, to place the square on the right spot. When you're copying the problem, to put the square, everything is going to be different. The derivatives, the integrals for these two functions, their graphs are different. Just go home and plug them into your calculator and see how different these functions are in terms of graphs. If the graphs are different, clearly the functions are different. And that's the part. So all of the trig plus ln's, they have this as a feature. The other functions you really can't, like x squared is x squared, right? You can't write that in any other way. Also e to the x is e to the x, and 3 to the x is 3 to the x. There's really not much else that you can do other than these letter functions, right? Any other questions, concerns? Okay. No blanket? Okay. Of course, here, right? Wow, I really made it clear. We should have like a pop test now. Can boost your grade since everything is so clear and no questions. Oh, save. No, you just saved everyone from having the pop.
So generally with f, in terms of these composition functions, is it like always going to be x and then just whatever is on the outside of like the most outer layer?
Yes, because the most outer layer. So this is going to be x cubed, and then you have ln x for g. So outer layer, and then dig deeper, dig deeper. We can chain 5 of these. So we technically never go past 3. So in calculus, the most complications that you are going to see are these types of functions with the, right, the 3-layer one. And then when you go to integration, 3-layer ones are not, generally 2. Like really spicy problems with the parameter section might have that. But yeah. Good. And the last part we need to touch upon are the inverse functions. So inverse functions, because we have trigonometric functions, and we have the issue that certain functions do not have inverse functions. Every function has an inverse. Every function has an inverse. But that inverse might or might not be a function. And unfortunately, it's not emphasized in pre-calculus a lot. So now we're not just reviewing, we're also broadening the concept of what you learned in your pre-calc, which will be needed here and there in calculus. So we have a notion of y equals f of x, which is a function. And the perfect example for something like this would be y equals x squared, which passes vertical line test, and we know it's a function, so it's all nice and cool, right? But then we talk about the notion of the inverse, and what inverse does is swaps domain and range. And the reason why it swaps domain and range is you want to create a function that will undo what you did with the function. I mean, let's just be clear. If you put in the notebook into your bag, you want to be able to take it out, right? And if you get into your car to go from point A to point B, you want to be able to get out of the car at point B, right? So certain actions which can be portrayed by functions need to be undone. Now, such is nature that some can't, right? So if I, right, do this, and then I use the eraser, I just undid my squiggle, and the programming allows for that type of inverse. I can also do this and go to undo button, and I have the same result, right? Now you program that into the matrix of all of these pixels that you have on the screen, and computer science is going to enjoy this real lot. And you guys get the matrix, and then you can do some kind of inverses and things, and right, it works. But there are situations where you can't do that. Let's say you're making a soup, and it calls for 1 teaspoon of salt. Now you misread that, and you use 1 snow shovel of salt. It's the same pan, all right? Yeah, is there an undo button on that? No, right? Unless you want to move your soup to a tub somehow, and because you have to dilute all of that salt somehow. But you get the idea. So not everything can be undone. Go ahead, break a vase, right? Go home, just smash a plate, right, into a countertop. See what happens, right? Where is the undo button on that one? No, right? No undo button. So certain functions are going to have inverse as a function, and others, right, to do the undo, and the others will not be functions. But certain ones we can fix, and others we cannot, right? So let's see. Swap domain and range means interchange x with y. So it's insanely easy to obtain these inverses. If we write y equals x squared, immediately x equals y squared, because that's where the swap happened, right? And then now you have to solve this for y. So you will square root both sides and make sure you put plus minus every time you square root both sides. Square and square root will die, and you get y equal plus minus root x. We know the graph for this, right? Not a function. So it's extremely easy to find the inverse. Now, this over here is the inverse of y equal x squared. And here in blood, but it is not inverse function. Because it's not a function. Look, right? Failed vertical line test. It's not a function. So is it inverse? Yes. Is it inverse function? No. And that is the part where pre-calculus doesn't really go into the level of detail. Now let's fix it. So use horizontal line test to predict inverse function. I put this in a box. So what was my original function? It was y equal x squared, and it looked like this. You see how it fails? Horizontal line test, HLT. Now that means inverse, yes. Inverse function, no. So do you have inverse? You always have an inverse. Now, since it failed horizontal line test, is it going to be a function? Nope, it's not going to be a function. So how do we fix it? We can fix this. I put fix in the quotation. By restricting the domain. So that f of x passes horizontal line test. Well, for my y equal x squared, I'm going to go from 0 to infinity. So what did I do? I have chopped off half of the function. You see the entire negative part, this line here, is gone. I only have 0 to infinity. This is 0, this is infinity, right? So I only have this part of the function to the right of the y-axis. Now that passes horizontal line test, as you can see, everywhere, which is the reason why I picked to cut domain that way. And we call this restricted domain. So now, when I do my swap x equals y squared and do all of that stuff, I will get y equals plus minus root x, but then there is no minus branch. So minus branch goes away, and I just have y equal root x. And that is this. So now it becomes a function. So by restricting the domain, we actually get to fix the issue of not having the inverse function. Now, before you go and say, what's the big deal? It's a huge deal. I told you, you get to do calculus on functions. You get to take the derivative of a function, the limit of a function, and the integral of a function. And guess what? What happens if you don't have a function? Well, you can sit in the corner and cry. Because you can't do anything. Well, you can do derivatives, but yeah.
Can you do the other side and like eliminate, like, can you do
Yes.
the other side and so you can do like negative infinity
to 0.
0
Yes.
instead of,
In which case you will just have a negative branch of square root and it will just go below. Right, so yes. Now, this is not a huge issue for x squared, no one cares pretty much, but trig is where we care a lot, actually. A lot of stuff is modeled by trig functions. Because trig functions are unlike other functions. Trig functions are periodic, which means they repeat itself, right? Each trig function repeats itself eventually. After 2 pi or after pi or whatever you do with the period of the function, eventually repeats itself. So this business of restricting domains is extremely important for those, because guess what? Some of your prime solutions for integration are inverse sine and inverse tangent. And if you don't have them as functions, well, you can already see what kind of help that can bring. So the only type of hell I would talk about here is obviously one where you can't do calculus, which fundamentally destroys everything we have as a species. It's in the base of everything. Guys, calculus was in 1600s. What was there before 1600s? Nothing. There was rubble, banging rocks to make fire, right, against each other to make the spark. They had bows and arrows and stuff. That's it. There was no banking. There was nothing. Okay, that was it. And then calculus, 1666, Newton and Leibniz, independently, 2 of them. The humanity was ready to move the next step, and that was it. And from that point on, you look around and you have what you have now, right? So if you don't have your inverse functions, you don't get far, right? So now, y equals sine x, and you are all used to its y equals sine inverse x, and you are familiar with that, right? Good. But don't you ask yourself, well, hold on. Sine x is this wave that goes on forever and fails horizontal line test miserably. So what the hell is going on there? Right? Well, of course, it's the game of a restricted domain. I can't do anything with this type of a sign. So what I do, well, what people did centuries before me, I just adopted it because it's true and it's good. We cut the sign from negative pi over 2 to positive pi over 2. There is more to this sign forever, right? It's going to be a wave that will go on forever. We throw all of that in the garbage, and we restrict our domain from negative pi over 2 to pi over 2, and then clearly the range is still negative 1 to 1. Ha! Now that piece passes horizontal line test, which means that we are going to have our sweet little inverse over here, which will have negative 1 and 1 on x-axis now, because negative 1 and 1 used to be on y. Remember, inverse swaps domain and range, swaps x and y. So if your y's were negative 1 and 1 on a function, then they become negative 1 and 1. And then these puppies here are negative pi over 2 and pi over 2. So we start here, and then drop down, rise up. There we go. Note that I'm putting these dots at the end to make it clear that it ends there. So this is the domain, and -1 to 1 is the range. Now that swaps over here, -1 to 1 is the domain, and -π/2 to π/2 is the range. Alright, so this should be good enough for you to just get started in thinking about these, and then you can do the cosine and tangent and all of the other guys. So you start with sine x, okay, it's infinite wave, fails horizontal line test, no inverse function. But do not despair. If you restrict the domain, you create a piece that passes horizontal line test, which does have inverse function, and the life is beautiful again. Meaning we can have our cell phones and gadgets. Real quick on tangent. You know the tangent graph. Goes like this. Has a vertical asymptote, then goes like that. Has another vertical asymptote, goes like that, right? So that's our tangent. That's what it does. Does it pass horizontal line test? Hell no, right? But then, if you use your domain restricting techniques and extract -π/2 to π/2 over here, now that will pass horizontal line test, and you will be able to get your tangent inverse graph, which is going to be utilized in your later. So generally I say to students, don't forget this graph. Right, so it's tangent flipped on the side, right? And you have your x-axis here, -π/2 and +π/2. That should be common sense because those were your asymptotes, to the left and to the right. And now they are your range, bottom and top, right? -π/2 and +π/2. That graph is going to pop up in your chapter 2 already. So it's a graph to know, and it's going to persist through Calc 2, Calc 3, differential equations, and so on. So if you don't know inverse tangent graph, yeah, you really need to know that one. Is there anything else that we should talk about? We can talk about a little bit about step functions. That's good. We'll talk about that. We still have time. I just want to mention the homework before I go into this very last thing. The first homework assignment, which is I believe already, or maybe not already, opened on the website, is review exercises of Chapter 1. So Chapter 1 is a pre-calc review. You are welcome to go and read all 5-6 sections that are there. Talk about functions, graphs, inverse, composition, all of the stuff, like trig. So everything that we covered here is in those Chapter 1. It's not a calculus, it's a pre-calculus, all of that. And the first homework assigned is obviously the homework there. Now in the textbook, I believe there are like 50 problems, right? Or 52, something like that. And generally, you know, someone is going to go, oh, you do 50 problems. Well, some people have to do 50 problems. The other ones probably would do 10, right? You need to do as many as you need to be okay with the material, right? To be good. And just drop all the nonsense about everyone is born equal and all this. We're not, okay? No one is born equal. We're all different. We have different abilities. And you have to make your peace with that. None of this nonsense about political correctness that we are born equal. We're not, all right? So, some of you are born with the wiring aimed towards learning mathematics like this. For you, lucky snowflakes, you will probably pick up 50% in class and do another 3 problems at home to score A. And then others might be challenged with math, good in something else, but challenged in math, and after 50 problems will be struggling for B. So there's your equality and those stupid arguments right in the toilet right there. It is not what, just simple like that. So don't ask me, do I have to do all 50 problems? No. If it's going to be 5 problems and you are going to score A in a class, hey, some of you will do 70 problems and you will still be going crazy not scoring A. And that's your lottery number, okay? So where was I? Maybe 20 problems per, section. That's where I stood. And then if the professor was really, like you have to have all the homework, of course, I'll do all the homework. So whether we're going to do 5 or 50 problems, I don't care. 50 or 52 are assigned because they cover the entire review session of Chapter 1. Now, you will notice text, which is set up for the problem, and then you will have maybe 4 or 6 or 8 problems that have the same problem statement. Well, you try 1 or 2. If it's going like this, you don't have to do all 8. You did 1 or 2, you're good to go, right? If you don't know the concept, well, hell yes, you do all 6 or all 8 to learn that concept. You need to know all of the concepts. So some of you are going to be really good in the inverse part and do 2 problems. Others are going to be terrible and do all 6 or 8. So there is no one size fits all. I will not police who did 5 problems and who did, because that's going to weed out immediately after the first test. Do not connect mathematics over here with smartness. You want to know if you're smart or stupid, you go take IQ test, okay? That's the measure for it, right? Over here, you did enough problems and you learned concepts, or you didn't. Now, some people will have to do 50 problems and score B, and another will take 2 or 3 problems and score the same B. And there you go. So that's the homework, and that's going to be the attitude for the homework. Online, I just don't want to see any zeros for the homework if you're doing homework online. Now, whether it's 5% or 100%, I don't care. Because I've seen students with 5% score A like this. And I've seen those with hundreds fail the class. So I've seen it all. Do as many as you need. And if you need extra, there is textbook, there is online, computer generated. And you know how many textbooks I have in my office? Infinite amount of problems, all right? That's all I do. I create problems all day. So if you need extra problems, talk to me and I'll hook you up, all right? The last part that I want to briefly mention is another type of, it's not a function, it's called piecewise function, which is a function that contains parts of many functions. So a good example of a piecewise function, let's say, would be f of x is equal to, let's say, 3 for all x's less than 0. Then x squared for all x's in between 0 and 2. And then negative x for all x's larger than 2. So this is what the piecewise function would look like. It's called piecewise because clearly you see 3 pieces. Those 3 pieces are partitioned through the domain, and each piece lives in its own domain. So if I want to graph this thing, I will start with the coordinate system, x and the y, and I will first draw these vertical lines to partition negative infinity to 0, 0 to 2, and 2 to infinity. Because the entire domain from negative infinity to positive infinity is chopped up into 3 pieces negative infinity to 0, 0 to 2, and 2 to infinity. Maybe I should write those also. You can write this one as negative infinity to 0. This one is 0 to 2 with the brackets that include those points. And then 2 to infinity. Right, these are the different ways to write these intervals, right? You can use inequalities, or you can use the sets. I mean the interval notation. So now, I have a function y equals 3, f of x equals 3. That's the constant line. So here it goes. And it's open circle over here because there was no equal sign. So this puppy here is f of x equals 3. Then we have a quadratic piece. Quadratic piece that will go, when you plug in 0, x squared is 0, so that's the origin. You plug in 2, 2 squared is 4, so 1, 2, 3, 4. And you have a quadratic piece over there. And then after 2, so in this third region, partition, you have negative x. Now negative x is a linear line that goes 45 degrees through the origin forever. Well, it's clearly going to pick up there and then go from there on, because you're not allowed to have that function here because it would fail the vertical line test, right? So it will pick up over here with the open circle, again, no equal sign, and then it will just go 45 degrees forever down. And that's the f of x equals negative x piece, and this one over here is f of x equals x squared piece. So we have three pieces, there are three different functions, constant, quadratic, and linear, right? There they are. And each one lives for that period of, you can say, time in the partition where they are assigned. The other example of this will be tax brackets. All right? Tax brackets are, again, a piecewise function. We call those step functions because they have only constant pieces. So I'm not sure what exactly what the tax brackets are now, but let's say this is 10%, and then the next one is 15%, and the next one is 25%, I know that for sure, and then 28%. So if you make 0, let's say to 10K, you have this piece over here. And if you are making 10K to, does anyone know? I mean, I can look up the exact numbers, but let's say to 30K, whatever. So to 30K, oops, open circle on that end. So to 30K, and then 30K to, let's say, I don't know, 90K. I don't know what the numbers are. You pay 25% tax. Over 90K you pay 28, and then you have, I think, 30, 33, 35, whatever the next tax brackets are. So it's a step function. Clearly your domain is partitioned 0 to 10,000, 10,000 to 30,000, 30,000 to 90,000, and those go on a side. And the percents will go. So if you are making this tax function in terms of unit is money, right? Tax function is going to be 10% tax from money less than 10,000. 15% money between 10K and 15K. You get the idea of what it was. So you can look at the function there, or you can look at the graph. Clearly, graphs easier to follow. They give the charts and tables. So actually, the table that you find online when you type in tax brackets, you get this, right? They give you the range for what money, the amount of percent you pay, right? That's what they give you. And then you can actually turn that into a graph and see visual for that. So those are step functions. And when you have a step function in a calculus, Well, if you have to, take the derivative, or you have to integrate, or you have to do something, well, that's like 3 separate problems, actually, in this case. So you will do the limit of this, or the derivative of this, or integral, and then separately, and then separately. So if you have piecewise functions, they're just going to give you more calculation. But it's the same as pretty much anything else. So you can practice also, drawing some of those, because we are going to actually use those a lot next class. So next class is on Saturday in a week, in this room at 8:30 in the morning. You guys will bring in class preps if you're interested in those extra points. Class preps are 2.1, 2.2, 2.3, 2.4. So first 4. And then please just make sure you have a title, which is CP, class prep. If you do it the homework on paper, HW, right? So CP 2.1, 1 page, right? And then on the back of the paper, you can do class prep 1.2, or if you use both sides, like my limitation is 1 sheet per lesson. Per section. Please don't hand in a class prep where you copy the entire book, right? Because copyright trolls are gonna lock you up for life. Do not copy the entire book. Definitions, theorems, examples, pictures, whatever makes you, but it has to be summary. The idea is short, sweet, to the point for you, all right? So 1 page or 1 sheet at most per lecture. Now, can you fit 3 on 1 page, front and back? Sure, you can put 3. Just make sure that I can find all of those titles quickly. Box them or something if you are putting a title mid-page somewhere. So CP 2.1, CP 2.2, CP 2.3, and CP 2.4 with your name. If you don't put the name, I auction it in class. Whoever wants to take it is fine. And whoever is the first one to say, I'm taking it, fine. Yes.
So that's all on the syllabus too, right? That's all listed. So PreCalc review on that, MyMathLab, and then the
syllabus gives you the code to access the MyMathLab. MyMathLab can be purchased directly on the website. You can purchase it right in a bookstore, or you can purchase it online, Amazon, I think. So there are ways to. Let me just say bye to these.